Hi, my name is Norbert Schmidt, and I'm presenting today our work-in-progress paper about energy efficiency analysis of compiler optimizations on the SPEC CPU2017 benchmark suite. More and more services are placed in the cloud these days, and this growing number of services are leading to an increasing amount and larger data centers. The NDC estimated that data centers will use about 140 billion kilowatt hours annually by this year. So they can be made more efficient by intelligently placing or consolidating services, minimizing resources through techniques like autoscaling while at the same time satisfying performance demands. The hardware can also be made more efficient through techniques like dynamic voltage and frequency scaling or different C states. But in the end, it's the software that controls the hardware. It determines what should be executed on the hardware and how it should execute it. So the running software has an influence on the energy efficiency of the complete system, that is the hardware and software combined. Different but functionally identical software can therefore have a different energy efficiency while the performance does not change. So our contribution in this work-in-progress paper is a first look at which factors make the software susceptible to compiler optimizations in terms of energy efficiency. We take a look at the programming language and the application domain. We base our analysis on the SPEC CPU2017 benchmark suite. The SPEC CPU benchmark is compute intensive. It has different code and problem sizes. The benchmarks are implemented in C, C++, and Fortran that cover multiple programming paradigms. The size ranges from 1000 lines of code to up to 1.5 million. It's with a CPU, memory, and compiler at the same time. It also has well-defined running reporting rules that help with repeatability. There are a total of 43 benchmarks that are organized in 4 suites: the SPEC speed suites and the SPEC rate suites. Both have the integer and floating point suites. The SPEC speed is measuring the time required to process one unit of work. This can either be single-threaded or multi-threaded. The SPEC rate suites measure the throughput of the system. Each of the 4 suites produces 2 metrics, the base and the peak. In the base runs, a benchmark that uses the same programming language or combination of programming languages must use identical compiler settings. In the peak runs, each benchmark can use different compiler settings, independently of its programming language. The basic setup for the SPEC CPU2017 contains 2 systems, the controller and the system under test. The system under test runs the benchmark and is connected to a power analyzer that collects measurement data, the current power consumption of the system. There's also a temperature sensor in front of the system under test that makes sure that the system is not running outside its specification. The data is collected by the controller and reported in the SPEC CPU2017 results files. First, we take a look if setting the compiler to increase performance can have an impact on the energy efficiency. We compare the relative values of base and peak run of the SPEC rate integer suite. We excluded benchmarks that have identical compiler settings for base and peak runs because they would report the same values and there would be no difference. We can see on the left side that optimizing for performance can indeed increase energy efficiency. If you take a closer look at one of the benchmarks that we have run, the 500 power bench R, on the left side of the figures, you can see that the runtime has decreased by 15% and the energy efficiency has increased by 5.5%. This difference can be explained that the average power has not increased proportionally to the reduction in runtime. As a next step, we take a look at how the implementation languages can influence if the energy efficiency improves. We use the 23 benchmarks from the SPEC rate integer and the SPEC rate floating point suite. We again exclude the benchmarks that report identical compiler settings. This leaves us with 16 benchmarks in total. As you can see in the table on the right, there are a total of 19 benchmarks reported. This is the case because 3 benchmarks are implemented in 2 languages, and we count them toward both of these implementation languages. We can also see that benchmarks that are implemented in the C language can be improved 100% of the time. For C++, it's still 85.7%. For Fortran, on the other hand, only 1 out of 4 benchmarks has improved energy efficiency if we use specific compiler settings for this benchmark that are meant to improve performance. This leads us to the question if C-like languages can be better optimized for energy efficiency. This in turn leads us to our null hypothesis. Are C-like and functional languages equally likely to show better energy efficiency? Here, at the 5% level, the null hypothesis must be rejected. This means that C-like languages and functional languages are not equally likely to show better energy efficiency if you optimize for performance. At the 1% level, the null hypothesis cannot be rejected. We can see the outcome of the Fisher exact test here in this contingency table. This outcome has three possible reasons. First, the compiler allows few optimizations for foreign programs. Second, functional programming provides an already energy-efficient programming style. Or third, our results are outliers due to the selection of benchmarks that we made. As a last step in our work in progress paper, we take a look at the application domain of the benchmarks. We use the same 23 benchmarks as before from the SPEC rate integer and floating point suits. We also exclude the 7 benchmarks that reported identical compiler settings. This leaves us again with the same 16 benchmarks as before. We group them into 4 application domains. The application domains are language transformation, modeling and simulation, artificial intelligence, and others. The grouping is considered on all 43 benchmarks of the SPEC CPU2017 benchmark suite. As we can see on the table on the right, that almost all application domains, language transformation, artificial intelligence, and others, can be improved. For modeling and simulation, only 42.8% of all benchmarks could be improved, as 3 out of 7. It must be noted that the grouping into the application domain is based on all benchmarks, not only the 16 benchmarks that we used in this evaluation. This means that our groups are skewed. As you can see in the third column of the table, the grouping, language transformation, and artificial intelligence are very small, while modeling, simulation, and others are larger groups. This could skew our results, so the current outcome is indecisive. In conclusion, data centers consume a large amount of energy. We should therefore aim to increase the energy efficiency as much as possible. We use the SPEC CPU2017 benchmark suite to check if the compiler settings, usually meant for increasing performance, influence the benchmarks in terms of energy efficiency. We checked if the programming language is responsible for this improvement or if the application domain is responsible for this improvement. The comparison of programming languages show promising results that C-like languages can be easily optimized when we use the performance settings in the compiler. The application domain, on the other hand, show non-distinctive results. So further measurements on a broader set of software are necessary. Thank you for your interest in our research. Feel free to contact us for questions or collaborations.